All right. We've been talking about fluids, and we're going to finish our fluids talking today. Now, once again, just to remind you, we are flying through this material. And so I don't expect you to get everything in depth, but I'm hoping that you're getting important aspects, things like knowing what density, what pressure is, why things float, what Archimedes' principle is. So in lab yesterday, you were studying Archimedes' principle, and hopefully you confirmed that, yes, the buoyant force is equal to the weight of the displaced water. Now, it would be nice if my graduate cylinders were able to measure the volume more precisely, because then you would have more exact matches. But hopefully that is sticking with you. And if you have questions, if you're like, I didn't understand that, make sure that you ask me rather than saying, well, there's another thing that I missed. All right? What?
Amber.
Not at all. I did not know that. By the way,
somebody go to HR.
Because, oh man. Because I mentioned it on Monday, Amber did get her flute back, and so we're all very thankful for that. Any chance any of the other people with stolen instruments got them back? Don't know, don't care?
They don't have external numbers. 2 violas, a trumpet, and a flute.
Did you say a tuba?
Viola.
Viola. Well,
2 violas.
2 violas. That's
stolen instruments?
yeah, a bunch of them.
It's like a violin.
Because people can sell them for good money.
Between a violin and a cello.
Stolen instruments?
Yeah, just people at the church. Now we have to lock them up in a Sabbath school room.
Hopefully, I would guess that it's the same person's.
There's cameras in the church, so I would go hunt them down.
There's a good chance one would think that the person stealing these instruments is the same one. So having found Amber's and having the pawn shop record of who sold it and everything, hopefully they can maybe find it. The pawn shop's required to keep that information. Anyway, let's talk more physics. Nathan was laughing because the student referred to this class as physics class. He says, not physics, it's physical science. But so far, it's been physics. Soon, you'll have a test on physics, and then this will become chemistry class.
Wait,
Then
we're going to test over all this material?
Over the physics section, and then over the chemistry section, and then over probably geology section, yeah. And then final exam will be over everything. Because, of course, the goal is that you'll be teachers someday, everyone except for Bryson, or except for Hosanna. Yeah, Bryson, we want you to be successful too. Yeah. And so as a teacher, you want to have this information and not just like, well, I sat in the class and took some tests. Yeah.
So are you going to bring us all, like,
I know, right?
are you going to bring us all, like, bouquets of flowers or, like, boxes of chocolate on our exam day?
Can you cancel lab because it's on Valentine's Day?
I'll be totally Forrest Gump and come in and say, life is like a box of chocolate. You never know what you're going to get. Okay. No, we can't adjust the schedule, even though Valentine's Day is very important.
I have a question. Oh! Do we have like a card of formulas or
No, I will give you all the formulas.
So will you give us like a note card, like a 4x8, or bigger about notes you have?
No, I figure giving you all the formulae is giving you what you need, and then the other things are the things that you hopefully have learned.
So like, what are your tests like? Fill in the blank?
They'll be all multiple choice.
No short answers at all.
None. Well, one. There'll be one.
Is
like the one on the scientific method will be a short answer question. But that's the only one. That is, by the way, the big chunk of your credit, right? It's more than 10% of the test, I think, is that question.
Is there a
what kind? It's just, what is the scientific method?
No, you'll have to list those 4 steps.
Okay.
And then I give you an observation, and then you have to apply those 4 steps to the observation.
Wait, so you have to come up with your own experiment?
You have to come up with your own idea for experiment, yes. Obviously, you're not going to be doing it.
Does that have to be a good experiment?
It has to be one that would test a prediction of a hypothesis.
Okay. Is it going to be like...
Will we understand the concept of the observation is over? Or like, will it be like really hard to come up with an experiment for the observation?
It shouldn't be, but that's a very personal question.
Okay.
Hannah has another question.
Is the review up on Moodle yet?
I think I have reviews up for the entire semester, but I will have to check to verify that.
Okay.
On Wednesday or Thursday of that week, when the test is, will we be going over like reviewing?
I believe there's a lecture that says review, and we'll be reviewing in that lecture. But I could be wrong, right? I'm not saying that's a dumb question because I said I believe.
Oh, it does.
I
It does say that.
Well, she has a question.
But other than on Moodle, they ain't saying review. Do you see kids up?
Oh, go ahead, yeah. Because if it's not, I'll write that on my hand too.
Why don't you just tell Siri to take a note? Oh, you don't have to watch it. I'm just kidding.
Yeah, I forgot it today. Okay, so really, let's finish talking about fluids, so we can move to our next topic. So pressure. What is the definition of pressure?
The measure of the amount of
It is. Does it say that up there?
Yeah.
Yes. But that's an important understanding, right? Like I said, when I was a kid, I was really confused about the pressure in a tire and how that relates to pounds of force. And it wasn't until I took physics class that I understood, so pressure is the force per unit area. Not the same thing, but they're related. So you can calculate force put on a surface from pressure by using, don't know why sometimes I get different views. Force is pressure times area, since pressure is equal to force over area. Now we talked about examples like putting the bowling ball on my hand. Other examples that are very common in physics test questions are things like, you have a little office worker who has a weight of 100 pounds, and she usually wears flat shoes in her office and there's no problem. One day she comes in and she's wearing these stiletto heels, and she starts putting holes in the floor, holes in the tile. Why is she putting holes in the tile when she wears her stiletto heels, but she doesn't when she's wearing her normal flats? More pressure because her weight is being concentrated in a much smaller area. And this is actually something real. Those stiletto heels can damage floors that are soft because you're putting a lot of pressure on. But we also talked about air pressure. And air is a fluid, something that flows. And so air pressure is the result on a microscopic level of the molecules bouncing off of things. So we have air flying all around us, and those molecules hit us and bounce off of us. And when they hit and bounce off, they change momentum. Right? Just like if a ball bounces off of the floor, it had initially momentum that was down, ends up with momentum up, so it has a change in momentum. And according to Newton's second law, a change in momentum divided by the time over which that change occurs is equal to the force. So those molecules bouncing off the walls or molecules bouncing off your skin, that's what's applying the pressure on your skin. And temperature, and I know I mentioned this because somebody already put this down as a potential test question. Temperature is a measure of the kinetic energy per molecule. Okay. It's the measure of the average kinetic energy per molecule in the gas. It's not a direct measurement, but it's a number that's proportional. Depends on the gas, what the proportionality is. If it's a monatomic either gas, it's a real simple proportionality. Other things, it can be more complicated. But temperature is telling you about the average kinetic energy, which, as the first time we brought this up, means that temperature is telling you basically how fast the molecules are going. If the molecules are going faster, when they bounce off of you, they're going to transfer more momentum, right? Right? So if you have the same number of collisions, but more momentum transferred per collision, then you can have a bigger force per unit time being applied to your skin, and that's a bigger pressure. So if the number of molecules stays the same, but you increase the temperature, the pressure is going to have to go up as well if you're in a fluid, because molecules are hitting you at the same frequency if you have the same number of molecules, but with a higher speed, hence putting a bigger force for each one. On the other hand, it doesn't always have to do that, because you could let some molecules escape. If you have half as many molecules and they're hitting you at twice the speed, you would have the same pressure, because you'd have twice the force for each of the collisions, but only half as many collisions per time.
There's some objects you can compress so much different to something else, like coal to diamond.
Yes, or things basically like if you compress ice at close to freezing temperature, it will melt into water. If you keep compressing, it'll turn back into ice, though, at a very high pressure. We'll talk about that later. I just read an article today that they found a third form of solid carbon, if anyone cares. Do you know what the forms of solid carbon are? There's graphite and diamond. And now there's this new one. I forgot what name they gave it, but it's totally cool. It's harder than diamond. And best of all, they can make it using the same type of lasers that I used to vaporize things when I was in graduate school. I did my PhD research on vaporizing stuff with these lasers, and now they're making stuff. Yeah, we should. Okay, so if you take a gas and you compress it, that piston is moving downward. And so anytime a molecule hits it, it's going to put a downward force, and it's moving downward. It's going to do work on the molecules. What happens to kinetic energy if you put work in? Or what happens to total energy if you put work in? It increases. So when you compress that, the kinetic energy is going to increase, because that's the only kind of energy they have. And since the kinetic energy increases, what is that going to tell you about the temperature? It's going to increase. You also are going to have then the molecules are having collisions more often, because there's less volume, hence they have to bounce around and hit surfaces more, and they're hitting harder. So if you have more collisions per second and harder collisions per second, what's that going to do to the pressure? Increase. So when you compress it, both the temperature should go up and the pressure should go up. But of course, the volume, the space it takes up, went down. Question, Hannah.
Why is the temperature increasing?
Increasing because you're doing, remember, work is force times distance parallel to that force. So if I push on Amber and she moves the direction I push against it, and she moves the direction I push, then I did work on her. And that's transferring energy.
Okay.
So her energy goes up, right? She'd go from stationary to moving. So this picture actually only says a few things. I said many more. If you cut the volume in half, that's what's illustrated here, then you are going to double the density, or you could double the amount of air and you double the density. Like if you put twice as much air in the same volume, it would double the density, is what that's saying. We have a number of relationships that build up to one final relationship. So we have Boyle's law, we have Gay-Lussac's law, we have Avogadro's law, we have Charles' law. And I'm not going to go through each one of those individually. I have slides for each one individually. If you want to, you can review the slides. You know the slides are available on below, right? But what I'm going to go to is what we get when we combine them all together. First, I have to talk about this one because I always think it's funny. When you drink soda with a straw, we always say that you are sucking the fluid up, right? But the fact is, you can't suck anything up. When you suck on the straw, what are you actually doing? You're lowering the pressure. You're lowering the pressure on the top of the fluid. You have atmospheric pressure pushing on the fluid in the top of the cup. And so atmospheric pressure is pushing it down on it. You've lowered the pressure here. So Pascal's principle, an important principle I haven't talked about, says that if you have a still fluid, which we'll treat our fluid as still, then the pressure anywhere in the fluid at the same elevation is the same. So the pressure inside the straw, I'll change to a lighter color. The pressure inside the straw there is the same as atmospheric pressure because it's the same elevation as the top of the water outside where atmospheric pressure is being applied. And so if you look at the fluid in the straw, you have atmospheric pressure pushing up at the bottom, well, at the water level. And then you have the pressure in your mouth pushing down at the top. But since you lowered the pressure in the top, force is pressure times area, you have a smaller downward force than the upward force. And so Newton's second law, net force is mass times acceleration, it's going to accelerate up. And so what you're actually doing when you're drinking out of the straw is you're lowering the pressure on the top so the atmospheric pressure can push it into your mouth. It's kind of interesting when you think about it that way. Atmospheric pressure did the actual pushing, it did the work. You lower the pressure so atmospheric pressure can do that. So if you were, I don't know, on the International Space Station, they sent you out to do a spacewalk. So you're in vacuum. Vacuum is when there's no pressure. That's an important term to know. Vacuum means no pressure. So if you have a little Capri or whatever they call those juice drinks that you can never stick the straw in, right? You have one of those and you're in space. Can you drink it on that spacewalk? No, because there's no pressure pushing in on it. You can't lower the pressure below zero, so you can't drink it. Now you can squeeze it, and that would create pressure inside to push it in. But you can't just drink it by sucking on it. You have to have something to push it. And since there's no atmosphere, you have to squeeze it to get the pressure to push it. Question?
I'm just curious because, like, I was on a plane before and they said that they can't serve straws on the plane. Is that one of the reasons?
No. It's probably the same reason when I was a kid we couldn't have straws in the school bus. Yeah, because if you have a straw in your mouth and you get in an accident, that straw can punch through. Soft tissue.
The cabins are pressurized, so it's not.
Yeah.
Well, the cabins are pressurized, but we talked about this a little, and I didn't, or Stu's talked about it, I didn't mention it. The cabin pressure in an airplane is not held at 1 atmosphere.
It's different ones, right?
They let it go down in pressure when you're up in the air because it's cheaper for them. And that's why you have things like, it's easier for people to get drunk on an airplane because of the lower pressure. Huh?
I mean,
I hope they wouldn't let you drink, Hannah. I wouldn't either.
No, I just know, I have a flight attendant, I know, and that's one of their rules, but yeah, that makes sense.
So they lower the pressure load. Since you have a flight attendant friend, you can also remind them that the atmosphere is and the Earth's magnetic field are protecting us from the radiation from the sun. There's lots of charged particles coming from the sun. And when you're at higher elevation, like my house in Colorado, you have less protection, so you're getting more radiation. And people who fly airplanes that are, like, 6 miles up, they're getting a lot more radiation than we do on the ground. So you can tell our doctor.
It's easier to get drunk in an airplane?
It is, yes.
So would it be easier to get drunk in Colorado than it would be in Florida?
Probably. It's also much easier to get high in Colorado.
That's true.
I saw a bumper sticker last time we were there. You came, got high, now go home.
Honestly, it's too crowded now.
Okay, you were going to ask a question, Wes? Oh, you.
Well, I wasn't asking to ask a question, but like, I was always wondering, like, if a cab, because when I was flying back from somewhere, I was really sick, and then my nasal were like all clogged, and then they basically like exploded.
Yes.
It hurt so bad.
And
I
that's
honestly thought
because
my
the
head
exterior
exploded.
pressure was lower. That's why.
Because, and it was like, I was fine, and then like halfway through, like, as soon as we like got to the high enough temperature, like an hour or so after the flight started, it was just like boom, instant. I was like, why? The calorie was pressurized, but I guess
Yes.
because it's cheaper, you love it pressure.
Right. That's exactly what happened. The air pressure is lower.
Don't fly when you're sick.
Don't ever fly when you have a migraine.
I couldn't wait 3 days afterwards either.
No, I had to go to the hospital because I went deaf for over a week and like there was like such bad pain. So like I flew back from France and then I flew to California like all within like a 2-day period when I was sick.
Like one of my blood vessels in my sinus froze.
Our place is all
Wow.
over the place.
Yeah, we are all over the place today. But you know what? We're having fun and learning things, right? Learning why she had a problem on her flight.
I have a question. So you
Yeah.
said that there's more radiation under the plane, or that was the exception?
No, there's more radiation.
Is that why they say you shouldn't fly, like when you have cancer or something?
I have not heard that.
Really? I always heard that, like, when somebody has cancer, they shouldn't travel on the plane.
I didn't know that.
Is the radiation
So there's
part
no
of
science to it.
I don't know.
I should have known about that radiation thing because my dad works in like the hospitals and he works on like MRI machines and stuff. And his radiation badge, whenever he flies, it alerts his work.
Really?
Yeah.
They're a little more careful then, because I was going to say, when I worked at the Department of Energy lab, we had a principal investigator. Okay, I was a graduate student. I did all kinds of trouble fighting this kind of thing. But principal investigator took his badge with him, flew to Denver, stayed there for a week, and flew back. And you can do the calculations. You're going to exceed what they tell you is the safe limit for working in the lab by doing that. And yet his report came back that he hadn't exceeded the safe limit. And he's
Well,
like,
my dad was wondering why it went off. He's like, I'm flying. And the people are like, no, it says you're working and like you're over. And it's like, if he goes over, it calls his boss. And if his boss calls him and he doesn't answer,
then they assume he's in trouble.
They call the ambulance and they're like trying to get his location and they can't get it because it's, you know, we were only on Wi-Fi internet on the plane. And so I should tell him that's why I'm not.
Yes, yeah, that's almost certainly why. Because you're getting more radiation.
That's interesting.
Okay, let's try to cover some physics today. Okay, so, Pascal's principle I already mentioned just through this. I don't know why I only have Boyle's law here. I thought I had the ideal gas law. The ideal gas law is the payoff for Boyle's law. Like I said, Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law combined to give you, and I'm sure this is in my slides somewhere. I just thought they would be here, and I'm writing them here because this is where they belong. I'm going to first write like this. The pressure of a gas multiplied by the volume of the gas is equal to that. Oh, I put NR. There's more than one way to write this equation. There's a lowercase n, a capital R, or a capital N and a lowercase k. N is the number of molecules, T is the temperature, and K is a constant. We use K for constant a lot. So this is pressure times volume equals number of molecules, and I will define molecule in just a second, times temperature times a constant. It's called the Boltzmann constant, but let's just say constant. So if you hold temperature constant, you get this Boyle's law. If you hold temperature constant, then pressure times volume is going to be constant, as long as the number of molecules remains constant. In physics class, we always keep the number of molecules constant. In chemistry, you don't. Now, what is a molecule is an important definition. Some of you know, some of you don't. A molecule is one or more atoms that are all held together. And we'll be studying this more carefully when we're doing chemistry. So, air is 79% nitrogen. Nitrogen is a molecule that's made of two nitrogen atoms bonded together, so they're traveling around as one piece. On the other hand, you have helium as a trace amount of air. Helium, a single atom, is a molecule. It's not bonded to anything. So a molecule can be one atom, can be multiple atoms, but they're all bound together and acting as one object. And so in this equation, it's the number of molecules, the number of objects bouncing around that we count. T is temperature, and we're going so slow today we might not get to it, but temperature is one of the things we're supposed to have here. In the United States, we use Fahrenheit to measure temperature. So we're very comfortable with the Fahrenheit scale. When I got up this morning, it was 18 degrees Fahrenheit. We got up yesterday, it was 5 degrees Fahrenheit. Got up on Tuesday, it was minus 10 degrees Fahrenheit. Right, so we know what these temperatures are. We know that's really, really cold, cold, and cold. But that's not the standard we use in science. In science, we use the Kelvin scale, not even the Celsius scale. The difference in Celsius and Kelvin is a constant offset. So when we use this, we need the temperature in kelvins.
Easy.
Easy, Hosanna says.
For you. It's not hard. Oh,
No,
really?
it's not hard.
Okay.
But if you're from any country besides the United States, it is a lot easier because they're used to using Celsius, and then you just add 273.15 to the Celsius temperature, and that gives you kelvins.
How about Fahrenheit? Well, Fahrenheit to Celsius
Then you
is more
gotta
complicated.
We'll go through that later in the lecture if we get there.
On the test, can you just give us everything in Celsius? Because then we can just.
No, because I might want you to convert.
Oh, I hate converting.
But that is one of the skills we want.
Are you from here?
Yes, she said she is.
Yes, but I took chemistry last semester. And you guys took
Hence, when we get to chemistry, you know who you should ask questions of?
I didn't take chemistry in high school, so I don't think it's fair that we have chemistry in here.
Most people didn't take chemistry or physics or geology in high school.
Yeah, no. I took the basics.
I took
Super math, and that's about it.
Okay, going back to the topic. So Boyle's law is if you hold the temperature constant. You could also hold the volume constant, and if you keep the number of atoms constant as well, if the volume is constant, if the pressure goes up, the temperature is going to have to go up. So that gives us another one of our relations. Or you can hold the pressure constant, and then if the volume goes up, the temperature goes up. The last one of the laws I named is Avogadro's law. That's dealing with the N. So this equation here helps us to relate those important variables that we use when we talk about, especially air, but when we talk about gases: pressure, volume, the number of molecules, and the temperature. We'll come back to this later, so it's not a finished equation yet. Okay, I talked about Pascal's principle that says that the pressure at any elevation is the same. So the pressure here and the pressure here is going to be the same if we have a continuous fluid. This leads to some funny things. I talked about firefighting yesterday, or last period. When I was at PUC, there was a fire in the Napa Valley, and there's a road here, and then there's a valley that goes here, and then there's a mountain that goes up there. And the fire was up the mountain. And so the firefighters are up here with their hoses, and the fire trucks are over here. And so, of course, the hose is going like this. So the engine operator knows how high the firefighter is above the engine, and he knows how much length of hose there is, so you know how much pressure drop you're going to have per foot, and you know that you have a pressure difference of density of water times G times the change in elevation. And so he calculates, I want to deliver 35 pounds of pressure up there, so I need the pump to be at this pressure. And that pressure is below the burst pressure for the hose, so he raises the pressure to that. And then the hoses all started breaking. The hoses were all bursting down here. Why were they bursting down there?
Because the pressure was way higher.
Because the pressure's higher, because you went down lower. It's just like if you were going down underwater, the pressure gets bigger as you go down, and down here the pressure was above the burst pressure for the hoses, and they started busting. And so basically, they couldn't fight the fire up there because they couldn't get water up there. So Pascal's principle says that the pressure change is zero if you stay at the same elevation. You would go up in pressure to go down here, stay constant as you move horizontal, but then go down as you come back up. And we use this to make another kind of simple machine. So here's another kind of simple machine, a hydraulic press. whether you are using a hydraulic system for the brakes in your car or for a jack to lift your car off the ground, it's the same fundamental principle. You take a fluid and you make a narrow area and you put a little pressure on there. Now the pressure is the force divided by the area. And so it doesn't take that much force to make this little pressure. But then you go to the other side and you make a really big area. So in the example of your car's braking system, you push on the brake pedal and you apply a force to that brake pedal that's going to put some pressure in a little tube that's like, quarter of an inch in diameter. And then that tube goes to the brakes where you have a piston that's like, let's say, an inch in diameter. If it's an inch in diameter, then its area, that's 4 times the diameter, square that, its area is 16 times bigger. So with the same pressure, but 16 times the area, you're going to apply 16 times the force to those brake pads than what you put on the brake pedal. Now, my numbers are just off-the-cuff numbers. I would be willing to bet that the actual mechanical advantage is bigger than that. They also use levers. You press on the brake pedal, and then you have a lever, so the actual force that you apply is magnified. You move the brake pedal this far, and you have a little plunger move that far, so the force is quite a bit magnified just because of that. So you have a couple different simple machines, but one of them is taking advantage of this action here to allow you to put a very big force on the brake pad with a relatively small force on the pedal, because people are pretty smart that way. So if we look at this example, let's obliterate that number and say how much, it's there as well. By now you all know the numbers. If I want to have 500 kilograms supported on the big side, how much force am I going to have to apply on the small side? Well, the first thing you do need to do is say the force. How does the force relate to the 500 kilograms? Force is weight, right? Force of gravity is weight. What's the equation for weight? It's mg. The force is mg, so that would be 500 kilograms times, and I'll put here 10 meters per second squared because it makes just the calculation easier. So we have a total of 5,000 newtons that we need over here. And so I'm like, the pressure here must be 5,000 newtons divided by, and it just says 50 area. So I'm going to put 50 times A, where A stands for area. It's a variable. So my pressure is, of course, 5,000 divided by 50 is 1,000. So my pressure is 1,000 newtons per area. Still don't know what area is, but I'll deal with that. So we come over here, and I have the pressure is the same, 1,000 newtons per area, but it's going to be the force in divided by that area. So now I can solve for force in, and this one doesn't take a lot of math. To get force in by itself, I have to multiply by area. So if I multiply both sides by area, I can cancel the areas. And the force in is 1,000 newtons. Did I do all my math right? No, this is 500. Whoops. There was the 0 there. It's 500. I did my math wrong there. Good. Because I was like, that doesn't work out. So the force in is 100 newtons. And then I can calculate what mass I would need using, again, force in is mg. So m is force in divided by g. So my 100 newtons divided by 10 meters per second squared. And I have 10 kilograms, which was shown there and there that I tried to obliterate. So this is basically what you're using when you have a hydraulic jack to lift your car at the service station. They have a little tube that they put let's say 35 pounds per square inch of pressure on the gas, the fluid there. Then it comes to a hydraulic ram that's much bigger, and you just take the ratio of the areas. If you go through the math, the ratio of the forces is equal to the ratio of the areas. So you make the ratio of the areas big enough that you can use that 35 pounds per square inch to lift the entire car. So it's a kind of simple machine that's using Pascal's principle as its basis. And we actually did work this equation out just now, but you probably didn't even notice it, right? Because when we said the pressure is the same, and the pressure here was force out over area, I didn't even write force out over area, and here was force in over area. That gives us this relationship. Force in over area 1 is equal to force out over area 2 for how the lift works. Okay. Now, fluid flow. This is kind of fun. It's one of I love physics demonstrations. I mean, why else do you take physics class if it's not for demonstration? Yeah. So this is a blow dryer. I wisely took it apart and disconnected the heating coil so it doesn't get hot. And it blows air. Don't have much hair, so it's not a big deal. Now, if you have air going through a pipe and it's continuous, that is, you don't have any bubbles or any scanning air, then you're going to have what we call continuity of flow. The amount of, in this case, a water pipe, so water passing per second is going to be the same everywhere. But if the pipe narrows, what's going to happen to the speed to get the same amount of water through per second? If I have a smaller area, what's going to happen to the speed to get it through? It's going to have to go faster. So we actually have what we call a continuity equation that says the area times the speed is equal to the flow rate, and that's going to be constant. So if the area of a pipe decreases, the speed has to increase. If the area of the pipe increases, then the speed's going to have to decrease. And this makes some interesting things. Bernoulli's principle gives us a relationship to relate these. You may or may not know the answer to this, but I'm going to illustrate it the very simple way. Blow air. I'm going to blow air over this paper. Well, do you know what's going to happen? Amber has an idea. Let's see. You have to get it flowing over the paper somewhat to make it really work. Okay. So clearly when I had the air blowing over the top, it lifted the paper. It was flapping because I couldn't get a steady stream. I had to aim it down here to get it going over the paper down here. Like this, it was not really going over the paper, not making a difference. So why would the paper come up when I have air blowing over the bottom? Or excuse me, over the top?
Because it changed the pressure.
Because it changed the pressure. Which way did it have to change it?
Had to lower the pressure.
It had to lower it so the pressure underneath is bigger than the pressure on top, and it rises. And so Bernoulli's relation says that when speed increases, pressure drops. Now this has some really interesting ramifications. I'm going to do a demonstration here just to make sure I get it done. So I'm going to turn this on again, put a little ping pong ball up above it, maybe. So I have a box of them. Okay. Right now, the ping pong ball is actually stable. It's not coming off the sides because air is blowing up here. Air is blowing up and hitting it, transferring momentum, making a net force to push up. That's why it's not falling. But air is also going around the side, and when it goes around the side, it lowers the pressure on the side. But since it's going around both sides, it's lowering the pressure on both sides. If it comes off to one side, then more air goes to the other side. The pressure is lower on the side it moved away from. Higher on the other side pushes it back. So now I'm going to tip it a little. And here's where I love this demonstration. What's going on now? It's going to fall eventually. What was going on when I tipped it? Okay, it became shakier, but it was still being levitated, right? It was air going like this, and the ball was going like this and staying there. Now, if you think about it, the air is pushing it to the left as you look at this picture. Why is it staying there? It must be that the air is going faster over the top. As gravity makes it drop down, you have more air going over the top, and your pressure on the bottom then becomes essentially atmospheric pressure. But on top, where the air is moving faster, the pressure is lower, according to Bernoulli. And so that lower pressure on the top is creating a force that's pushing it up and a bit to the right because of the directions, so that it doesn't go shooting out. So it's this Bernoulli relation with moving wind having a lower pressure that allowed me to do that. Now the picture that Amber wanted to see.
I want to go back to the other side.
Oh, you wanted me to go this way?
Yeah.
Why?
Finish the notes.
Okay. They are finishing their notes. While they're finishing their notes, when you have high wind speeds, well, one of the first things you notice is that, it picks up small animals and trees and whatnot, throws them around. Tornadoes can do things like lift up a house from Kansas and drop it in wherever the Wizard of Oz is. Tornadoes, what's the essence of a tornado as far as you're concerned? They are air doing what? Swirling in a circle, so it's moving really rapidly. And according to Bernoulli, that air is moving really rapidly. What's that doing to the air pressure? It's lowering it. So when you have those high wind speeds, you lower the air pressure. Can I change it now? So here we have a house that has air inside that's still. So that still air is going to be at your standard atmospheric pressure. But you have air blowing over the top very rapidly. And so the pressure on top is lower than atmospheric pressure. If you have higher pressure inside and lower pressure outside, what happens? It pushes the roof up. That's how you can lose your roof in a tornado, because the lower pressure on top lifts it up. It acts exactly like an airplane wing. This is how an airplane flies. When I was in grad school, I thought it was funny to sit on an airplane, look out the window, and then explain to the person sitting next to me what keeps an airplane in the air. Because when you realize it's just because air is going faster over the top, it starts to become a little more shady. You just say airplanes fly, but then when you find out why, wow. It's the same thing that takes the roof off of a house in a tornado. And of course, some people say, well, why don't you just open the windows of your house so you have air flowing through your house? Well, I suppose you could try doing that, but it probably costs a lot of damage to your house if you did that too. So probably not a good solution. And of course, houses are generally created to keep the roof from falling down on the house, not to keep the roof from flying up off the house. And even if you make it so it's going to keep the roof from flying up in the house, it's still going to be then working on picking up the entire house, just like in The Wizard of Oz. So the damage we see from tornadoes is because of this lower pressure, well, the damage of roofs being lifted off, cows flying by. It's because the lower pressure in the moving wind causes them to be lifted up, and then they just get thrown around by the wind. So that Bernoulli relation, very important for how this occurs. And there is the airplane wing to finish up. What was mentioned by Bryson. In an airplane wing, the airplane wing design has a number of important features. The first one is a smooth, blunt front edge. It needs to be smooth and blunt, not sharp, because if it was sharp, it would just split the wing on that angle. What you want is it to be blunt so the air will split differently depending on what angle the wing is at. And then the next important thing is the top of this wing is longer than the bottom. So the top of the wing has an effective length that's that long. The bottom of the wing has an effective length that's that long. The red line is longer by, let's say, 10%. Or excuse me. Yeah, the red line is longer by about 10%. The air molecules, when the wind comes through, the air molecules, as seen by the Earth, were just stationary. The wind comes through and they basically just go like that, come back together. Basically, not exactly. But if you are in the airplane's reference frame, those molecules, one of them went up and over the longer surface of the top, and at the same time the other one went under the shorter surface on bottom. So the speed of the air on top of the wing was faster than the speed of the air under the wing. If the speed on top is faster, then what does that tell you according to Bernoulli's relation? Faster speed means lower pressure. So the shape of the wing having the top longer and the bottom shorter makes it so there's lower pressure on top than on bottom. And so then the area of the top, the area we call the cross-sectional area, if you were to just look straight down and measure the area that you see, and then look straight up from the bottom and measure the area you see, they're going to be exactly the same. So they have the same areas, but more pressure on bottom, less pressure on top, hence more force pushing up on the bottom than you have force pushing down the top. The difference in those two we call the lift. So the lift has to do with the speed of the airplane and the speed of the air over the top and the speed under the bottom. So the faster an airplane goes, the higher those speeds are going to be, the bigger the lift. So airplanes at higher speed are going to have more lift. At lower speed, less lift. Well, we like to do things like land airplanes. It's kind of fun to land. And I mean, it's kind of fun because then you don't have to stay at the airplane anymore. You can go do things. But in order to land,
is that why those things come out?
That's exactly where I'm going. Those things come out to make it have a bigger area to give you more lift. So that you can go at a slower speed without having a wing stall. A wing stall is when you have the upward force is not big enough. Well, the difference in the two forces is not equal to the weight of the airplane. The weight of the airplane is bigger than the lift. Suddenly it falls out of the sky. That's a wing stall. And so they extend the wing so that you can fly at a slower speed and still have enough lift. And the goal is to get like 3 feet off the ground and then slow down to the point where you have a wing stall and you hit the ground and you're done. All right. It is time for us to get ready for the Sabbath. Have a great Sabbath day.